The James Webb Space Telescope is the best and the most powerful space observatory in the entire universe. Just a day after it was switched on, Webb made a staggering discovery. NASA's $10 billion space telescope discovered the most distant and ancient starlight yet observed. It successfully uncovered an undiscovered country of early galaxies that were present close to the Big Bang, the beginning of the universe, 13.8 billion years ago. This discovery was easy for Webb because of how significantly designed it is to find infrared light that has been stretched through time and space. This is quite impressive, but will Webb be able to prove the Big Bang Theory wrong? If you're curious, we'll advise you to stay tuned because that's what we'll be uncovering in this video. Though what we observe is the expansion of an endless world, Big Bang conjures images of a firecracker going off at a specific moment and location, with a center. Some scientists contend that the Big Bang is a seriously misleading phrase for the expanding world that we observe because the universe doesn't have a center. Nonetheless, its idea is both straightforward and simple to misunderstand. The Big Bang was a process, not a single event in time, that occurred everywhere at once. We are aware of this because, 1, galaxies are moving away from one another rather than toward a central point, and 2, the cosmos is uniformly heated due to early cosmological heat. So now that you understand the Big Bang Theory, you might be thinking, so scientists want to see the beginning of the universe using the Webb? How possible is that? It's not an impossible task, especially if you're judging by Webb's track record. It made history on July 12th when it unveiled its first image, a gem-filled picture dubbed the deepest picture of the universe ever taken. The telescope can look back in time, farther than any other telescope, observing far-off stars and galaxies as they appeared 13.5 billion years ago, not long after the beginning of the universe as we know it. What makes this possible? What enables a machine to see back in time? It's not rocket science. Oh, it is, but it's not magic. Though it sounds magical, it's simply the way light works. Now to the big question. After Webb made its first and very impressive discovery on July 12th, the question everyone has been asking is, will the Webb telescope see the Big Bang? Although we cannot see the Big Bang itself, we can see the heat that existed approximately 380,000 years after the universe's expansion, which is what we refer to as the Big Bang. The universe and the sky are both filled with this heat. In actuality, it still does. With the help of satellites that NASA and ESA have developed, including Planck, the Cosmic Background Explorer, COBE or COBE, and WMAP, or WMAP, they were able to map it. The only temperature variations at this time were very slight, and the cosmos was incredibly smooth. COBE, WMAP, Hubble, and Planck all saw farther back than JWST, which was built to observe a time of the universe's history that has not yet been observed, not the universe's origins. We are particularly interested in the first items that emerged as the cosmos began to cool following the Big Bang. The period for which COBE, Planck, and WMAP were designed is maybe hundreds of millions of years later. The exact moment the cosmos created the first stars and galaxies, or even how it did so, is unknown. So, JWST was built to answer these questions. The initial creation of the chemical building blocks of life took place in the first generation of stars that emerged after the Big Bang. We need to know how it happened since they are the reason we are here right now. NASA is still unsure despite its theories and projections. However, one way in which the early stars must have affected the course of history is through the production of other chemical elements in addition to hydrogen and helium. Hence, if we measure what occurred in the beginning, we will understand where our atoms came from and how the little planet Earth became capable of hosting life. The Big Bang's heat signature was first detected by the microwave COBE and WMAP satellites roughly 380,000 years after it took place. However, there were no stars or galaxies at that time. In actuality, the universe was a rather gloomy place. The universe was like a boiling soup of particles after the Big Bang. Protons and neutrons started fusing to form ionized hydrogen atoms as the universe began to cool, and eventually some helium. The ionized hydrogen and helium atoms attracted electrons, converting them into neutral atoms, which for the first time prevented light from being scattered by free electrons. The universe wasn't as mysterious anymore. But before the first light sources began to form and put an end to the cosmic dark ages, it would still be some time, maybe even up to a few 100 million years after the Big Bang, before the universe began to shine. We still don't know how exactly the first stars in the universe, the ones that fused existing hydrogen atoms into additional helium, appeared, or when they originally originated. Thankfully, it's one of the questions Webb is to assist us in addressing, so we will find out eventually. Wondering why we have so much faith in Webb? It's because to see these first stars and galaxies that formed in the universe, we need a powerful infrared observatory key. Still don't get it? Okay, we'll break it into bits. We want to view these objects as they were 13.6 billion years ago, when light first entered them. Think of the light reaching our telescopes from the first stars and galaxies 13.9 billion years ago. By the time this light gets to us, its wavelength or color shifts toward red. This is what we call a red shift. Red shift is the concept that the light that these early stars and galaxies emit, whether it be visible or ultraviolet, actually shifts to redder wavelengths by the time it reaches our current location. Most of that visible light is typically displaced toward the near and mid-infrared region by the electromagnetic spectrum with very high red shifts, i.e. the farthest objects from us. Why? In this instance, it's because Einstein's general relativity comes into play when discussing extremely far-off objects. It explains that the universe expands. Things, or in this particular case galaxies, travel farther away from one another as the distance between them widens. Additionally, any light in that area will stretch, changing its wavelength to a longer range. Because this light travels to us as infrared light, it can render distant objects very faint, or worse still, undetectable at visible wavelengths. So we need a strong near and mid-infrared telescope to observe the first stars and galaxies. And that's exactly what Webb is. About 100 to 250 million years after the Big Bang, we'll be within Webb's field of vision. Additionally, it will cover several important issues like when and how reionization happened to help piece together the history of the creation of cosmic structures. What factors led to reionization? And what the first galaxies are. How? It's pretty simple. Webb will perform ultra-deep, near-infrared surveys of the cosmos to discover the first galaxies, and then use low-resolution spectroscopy and mid-infrared photometry, which measures the intensity of an astronomical object's electromagnetic emission to confirm the results. High-resolution, near-infrared spectroscopy will be required to analyze reionization. It's JWST we are talking about here, the same telescope that uncovered an undiscovered country of early galaxies that were close to the Big Bang. The photos from James Webb are a turning point for humanity, particularly because they disclose information about our universe that will guide the development of gravitational physics in the future. With unmatched accuracy, James Webb has already photographed a quintet of black holes. Not just one, not two, not even three, but 5. These pictures might show how the black holes merged and congregated in the early cosmos. This fresh insight might help solve the puzzle of black hole jets. The cameras on Webb can travel far back in time and into deep space. The furthest distance we have ever observed in space is 13.6 billion light years, which Webb is capable of seeing. Thanks to a space-time ripple that results in high magnification, researchers using the James Webb Telescope, JWST, have captured images of the farthest distant star ever spotted. Its light has traveled 12.9 billion years through JWST's optics, from its present distance of 28 billion light years distant. James Webb will reveal some of the greatest mysteries of our universe by using cutting-edge equipment and expanding Hubble. For space telescopes, visual clarity or angular resolution is everything. JWST is certainly no slouch in that regard. A US coin could be seen well by the telescope from a distance of about 24 miles. Or, to put it another way, JWST could detect a football from a distance of about 340 miles. So James Webb Telescope has not been able to prove the Big Bang Theory concretely yet, but soon, it is only a matter of time before it does.